Hello everybody. In today's class, we'll discuss the points which are related to inductors, and those are nothing but we'll learn what is meant by mutual inductance and coefficient of coupling. Okay, so the learning objectives for today's session will be the continuation of the previous class, and we'll try to learn the expressions related to mutual inductance and as well as coefficient of coupling, and we'll also know what is this coefficient and what does it affects, and how does it affects any inductor. Okay, so in the previous class we have seen that the inductor that generates an induced EMF within itself as a result of the changing magnetic field around its own turns. When this EMF is induced in the same circuit in which the current is changing, this effect is called as self-inductance, right? So this is a point we have discussed in the previous video. That is, if a coil is supplied with a voltage and if the coil is given with a current, supply of current, the ability to induce voltage in itself is called as self-inductance. That is, the ability of a coil to induce voltage in itself is known as self-inductance, and it is indicated by a letter L, and the units for the inductance is nothing but henries. So these are the points which we have discussed in the previous video. So in today's video, so an additional version of inductance will be discussed, that is mutual inductance. So when an EMF is induced into an adjacent coil which is situated near with the same magnetic field, the EMF is said to be induced magnetically or inductively or by mutual inductance, right? So when a current carrying conductor, and in a current carrying conductor, or when one coil is placed near another coil, an EMF when is induced in the secondary coil because of the EMF induced in the primary coil, and this property is known as mutual inductance. That is, we supply energy to one coil, the first coil, which is placed near another coil. So when energy is supplied to the first coil, because of the voltage induced in the first coil, here you can see here, an EMF will also be induced in the second coil. That is nothing but, here I have taken it as L2. L1 is the first coil, L2 is the second coil. Because of the voltage in the first coil, an EMF will be induced in the second coil, and this property is nothing but mutual inductance. In general, mutual inductance is indicated by a letter M. Self-inductance or simply inductance we indicate by letter L, whereas mutual inductance is indicated by letter M. So when two or more coils are magnetically linked together by a common magnetic flux, then they are said to have a property of mutual inductance. Okay, I repeat, when two or more coils are magnetically linked together by a common magnetic flux, then they are said to have the property called as mutual inductance. Okay, so the point where we use this mutual inductance is, so mutual inductance is the basic working principle, or it is the operating principle of devices like transformers, motors, generators, and also in any other electrical component that interacts with any other magnetic field. Okay, so mutual inductance is a property where we observe when we see more than one coil connected in any circuit. That is, in general we see this property in transformer, right? So the combination of two individual coils, we call it as a transformer, right? So there we use mutual inductance. Okay, and even in the motors, generators, we use mutual inductance principle. So we can now define mutual inductance as the current flowing in one coil that induces a voltage in the adjacent coil. So concept is very simple, that is the current what is flowing in the primary coil will induce a voltage in the secondary coil, and that property is called as mutual inductance. But here the point to be noted is mutual inductance can also be a bad thing, like it is called as stray or leakage inductance from a coil and can interfere with the operation of the another adjacent component by means of electromagnetic induction. Got the point? So not all the times mutual inductance is considered to be good. Sometimes it causes some interference with the adjacent component, and that we call it as by means of electromagnetic induction. So from the electrical screening to a ground potential may be required. Okay, so solution for this is nothing but some any kind of electrical screening to a ground potential is required to avoid this stray to avoid this stray or leakage inductance. Okay, so the amount of mutual inductance that links one coil to the other coil depends very much on the relative positioning of the two coils. Okay, so how much amount of mutual inductance is developed in the secondary coil is dependent on the placement of the two coils. For example, if one coil is positioned next to the other coil so that the physical distance apart is small, then nearly all the magnetic flux generated by the first coil will interact with the coil turns of the secondary coil, inducing a large EMF and therefore producing a large mutual inductance value. Okay. Likewise, if we take two coils which are far away from each other or at different angles to each other, that is when the two coils are placed at two different angles or if they are placed apart from each other, then the amount of induced magnetic flux from the first coil into the second will be weaker, producing a small induced EMF and therefore much smaller mutual inductance value. So the effect of mutual inductance is very much dependent on the relative positioning or spacing of the two coils. Okay, is it clear? That means if you take two coils and if you place them together, not all the times you find the same amount of mutual inductance in the secondary coil. The if you want to the amount of mutual inductance that is being induced in the secondary coil is totally dependent on the position how you place the two coils, right? So when they are close to each other, that is when two coils are close to each other, the mutual inductance will be more. When the two coils are separated or far away from each other or placed at some angle to each other, the amount of EMF induced will be small. Okay, so you have to keep it in mind that not all the times the same coils will give us the same amount of mutual inductance, right? So though same inductors when placed at different positions will develop different mutual inductance. If you want more mutual inductance to be developed, place them together or side by side. When you don't want a higher value, or if you want a lower value of mutual inductance, simply place them far from each other. Then the value of mutual inductance automatically drops. Okay, got the point? So if you can see this explanation, this coil. So here there are two coils. There is one coil named L1, another coil named L2. Here you can see that the distance between the two coils is less when compared to this diagram. So in this also, the mutually coupled coils, here it is very short, whereas here there is a large distance between the coils L1 and L2. Here we call it as the magnetic lines of flux are wider here, when as you can see it on the screen. So the mutual inductance that exists between the two coils can be greatly increased by positioning on them on a common soft iron core, or by increasing the number of turns of either the coil as wound in a transformer, right? Either by increasing the number of coils turns, or by uh, positioning them on the same core material, we can increase the mutual inductance. If the two coils are tightly wound one on the top of the other over a common soft iron core, unity coupling is said to exist between them, as any losses due to the leakage of the flux will be extremely small. Got the point? That is, not all the times we take two different core materials and wound a coil on two different cores. So if you want to increase the amount of mutual inductance, you can use a single core on which you can wound two inductors on the same core, either side by side, or if you want to increase the amount of mutual inductance further and reduce the amount of leakage, you can wind the coils one above the other on the same core, such that the leakage of the flux will be extremely small. So then, by taking a perfect flux linkage between the two coils, the mutual inductance that exists between the two coils, then we can simply write it as M is nothing but the mutual inductance. Okay, M is equal to mu naught mu r N1 N2 A by L. So here all the terms we know, like M is nothing but the mutual inductance in henries, mu naught is nothing but the permeability of the free space, and it is a constant value, and it is given as 4 pi into 10 power minus 7, whereas mu r is nothing but the relative permittivity of the soft iron core. N1 is the number of turns of the coil of the inductor L1. N2 is the number of turns of the coil for the inductor L2. Whereas A is the cross sectional area in m square, and L is the length of the coil in meters. So here I am taking only the area of cross section A common here, because I am considering the same coil and on the same core. So that is why I consider it as simple A only. So this is the expression for mutual inductance of the coils when they are connected on a single core, or if you want them on a one above the other. Then the mutual inductance is this formula: M is equal to mu naught mu r N1 N2 A by L. Here the other point to be noted here is that mu r, that is relative permeability, will be varying according to the core material. So as we were discussing in the previous video, that inductors can be either air core, iron core, or ferrite core, right? So depending upon the core material, So by depending upon the core material, the mu or relative permeability will vary. For each material, relative permeability will be a different value. So considering those points also in mind, you can choose the core material for the inductor. Okay. Now we'll see what is meant by mutual inductance, mutual induction, what is meant by mutual inductance, that is how we write the mutual inductance term, and later what is the amount of self inductance in the two different coils. Like here in this diagram, we have taken a coil, two different coils on a single core. Now what we'll see is how the value of M is dependent on L1 and L2. That is, here in this expression I have given the value of M without any dependence on the value of L1 and L2. Now we'll try to derive or get an expression for M where M is dependent on the values of self-inductance of the first coil L1 and the self-inductance of the second coil L2. So based upon these two values, we'll try to find out the mutual inductance of the two coils. Okay, so here in this diagram, I'll show you one diagram. Here you can see I have taken a core on which onto the left side I have wounded a coil with some number of turns N, and this inductor has been given a name L1, whereas the second coil L2 is wound onto its left side, onto its right with a number of turns of N, and both the coils are wound on a same core with a cross sectional area of A, and here I have taken a space between the L1 and L2 as S. Now we'll see how we can write the mutual inductance for this particular coil. Okay, so here the current flowing in coil L1 sets up a magnetic field around itself with some of these magnetic field line passing through the coil 2. Okay, so L2 gives us mutual inductance. Got the point? I repeat. So the current that is flowing in the coil 1, that is L1, sets up a magnetic field around itself with some of these magnetic lines of field passing through the coil L2, giving us some mutual inductance. That is, when a current is flowing, L1 develops some self inductance and also it develops some mutual inductance in the coil L2. The coil has the current of I1 and the number of turns as N1, and the coil 2 has the number of turns as N2. Okay, N1 is the number of turns for the first coil and N2 is the number of turns for the secondary coil. Therefore, we can say that the mutual inductance M12 of the coil that exists with respect to the coil due to coil 1 depends on their position with respect to each other, and it is given by this expression, that is M12 is equal to N2 pi 12 I1. Okay, so here you can observe that I have written here as M12. Why M12 means because of the first coil and EMF is induced in the second coil. So this mutual inductance is because of the first coil. That is why I have written here as M12. This mutual inductance is dependent on the number of turns in the secondary coil or the second coil and flux that is getting linked from first coil to the second coil. So that is why I have written here as pi 1 2, and it is dependent on the current. So here the current that is flowing is nothing but the current that is flowing in the first coil, that is L1. So we can simply write it as I1. So M12 is nothing but the mutual inductance because of the first coil L1. So M1 is nothing but the inductance, mutual inductance because of the first coil L1. So and we can write it as N2 pi 1 2 divided by I1. So like in the similar way, we can write the flux linking coil 1 L1 while the current flowing into the around the coil 2 L2 is exactly the same as a flux linking the coil 2 through the same current flows around the coil 1 above. So then the mutual inductance of the coil 1 with respect to coil 2 can be defined as M21. Got the point? So now we have written it as M12 because of the first inductor or L1, mutual inductance is developed in the second coil. That is why we write it as M12. Now there is another point, we call it as M21. So M21 is nothing but because of the self-inductance that is developed in the second coil, there occurs a mutual inductance in the first coil because of the second coil. Okay, so that mutual inductance will be indicated as M21. So that will be the same as this expression but with a varying terms, like M21 can be written as N1 pi 21 divided by I1. Here current is almost the same current. So this mutual inductance is true irrespective of the size, number of turns, relative position or orientation of the two coils. So because of this, we can write the mutual inductance between the two coils as M12 is equal to M21 is equal to M. Okay. So what I am trying to say is that because of the first coil, mutual inductance will be induced in the second coil L2, and at the same in the same fashion, because of the self inductance of the second coil, a mutual inductance will be developed in the first coil. So this is called as M21. So vice versa will be there, that is one self inductance, and because of that self inductance, mutual inductance in the adjacent coil will be developed. So M12 will be equal to M21, which we call it as simple M. So then we can see that the self-inductant characteristics of an inductor as a single circuit element, while the mutual inductance signifies some form of magnetic coupling between the two inductors or coils depending upon their distance and arrangement. Okay, so because of the arrangement and circuit elements, mutual inductance will be developed, and the self inductance of the each individual coil, if we take, can be written as L1 L2, as two different terms can be written as L1 is equal to mu naught mu r N1 square A divided by L, whereas L2 can be written as, that is L2 is nothing but the self inductance of the second coil, can be written as mu naught mu r N2 square A by L. Okay, so for both the coils we can write the self inductance and we can write mutual inductance also. So as we know, you know what is meant by mu naught mu r, right? Absolute mu naught is absolute permeability, mu r relative permeability. N1 is the number of turns of the first inductor L1. N2 is the number of turns of the second inductor. A is the area of cross section of the core. L is the length of the core. Okay, so now if you want to simplify this expression and get the terms in terms of and if you want to get the expression in terms of M, L and L1 and L2, then what we do is just we cross multiply these two expressions. Okay, the mutual inductance that exists between the two coils can now be expressed in terms of self inductance of each of the coils. So if we cross multiply this L1 and L2, then we get M square is equal to L1 into L2. Okay, M square is equal to L1 into L2. If you want to remove that square term, you can give it as a square root for L1 and L2. So the final expression for mutual inductance in terms of self inductances, we can write it as M is equal to square root of L1 L2, and units for mutual inductance is same as self inductance, that is henries. So M is equal to root of L1 L2 henries. Okay, got the point? Now we'll try knowing these points like what is meant by M, what is meant by L1, what is L2. Now we'll discuss what is meant by coefficient of coupling. Okay, till now we got to know that because of the self inductance in L1, mutual inductance will be developed in L2, right? And because of the self inductance of L2, mutual inductance will be developed in L1, right? So these are the points what we have discussed till now, and I have shown you an expression which gives us what is meant by M, what is meant by L1 and what is meant by L2 has been given in this till now. Now we'll see what is meant by coefficient of coupling. Okay, so the above expression assumes, that is this expression M, this expression is written considering that there is zero flux leakage and there is 100% of magnetic coupling between the two coils, that is L1 and L2, right? So without any losses or with the 100% of magnetic coupling, we have given this expression as M is equal to root of L1 and L2. But in reality, what happens is there will be always some loss due to the leakage currents that occurs between L1 and L2, and also because of the position. So in the starting of the video I was telling you that the amount of mutual inductance that can be developed will be dependent on the placement of the coils, right? So based upon the position of the coils and also because of the leakage factors, we can say that this expression may not prevail. So the magnetic coupling between the two coils can never reach or exceed 100%, but can become very close to these values in some special inductive coils. So if some coils of the magnetic flux linkages with the two coils, this amount of flux linkage can be defined as the fraction of the total possible flux linkages between the coils. This fractional value is called as coefficient of coupling, and it is generally indicated by the letter K. I repeat, sum of the total magnetic flux linkages with the two coils. This amount of flux linkages can be defined as a fraction of total possible flux linkages between the coil, and this fractional value is called as coefficient of coupling, and it is given by the letter K. In generally the amount of coupling that exists between the two coil is expressed as a fraction number between 0 and 1 instead of any percentages and all. Okay, where 0 indicates no inductive coupling and it is called as loosely coupled. Got the point? So if the coefficient of coupling is 0, then we say that the two coils are no way coupling to each other. That is, no inductive coupling is there between the two coils. And if the coefficient of coupling value is 1, then we can say that it is showing a maximum inductive coupling or full inductive coupling is there when the coefficient of coupling is 1. That is, we simply say that the two coils are now tightly coupled to each other. Okay, in general, in other words, what I can say is, if K is equal to 1, the two coils are perfectly coupled. If K is less than greater than 0.5, the two coils are said to be tightly coupled, and if the K value is less than 0.5, the two coils are said to be loosely coupled. Then the equation above, which assumes the perfect coupling, can be modified to take into account this coefficient of coupling K as K is equal to, we can write it as, you can see here, M is equal to K into root of L1 and L2. So if you want to take just know the value of K, we can write it as K is equal to M divided by root of L1 into L2. When the coefficient of coupling K is equal to 1 or unity, such that all the lines of flux of one coil cuts all the turns of the second coil. That is, the two coils are tightly coupled to each other and the resulting mutual inductance will be equal to the geometrical mean of two individual inductance of the coils. Also, when we see that when the inductors of the two coils are same and equal, if L1 is equal to L2, if that is the case, the mutual inductance that exists between the two coils will be equal to a single coil, right? That is if we write if L1 is equal to L2, then we can simply write it as L square. So if L square and square root gets cancelled, then we simply will be simply left out with the term M is equal to L, right? In such case, that when both the coils, that is when both the self inductances of the coils L1 and L2 are same, the mutual inductance will be equal to the self inductance. So then we can write it as M is equal to L, as L1 and L2 are both the same. Okay, got the point? So this is all about coefficient of coupling, that is how much the amount of inductances occur when two coils are nearby to each other. That is, what amount of fraction the inductances are being developed from one coil to other coil. That fractional value that is indicated by a term called as coefficient of coupling, and it is given by an expression K is equal to M divided by root of L1 and L2. Just by knowing the mutual inductance and the values of L1 and L2, we can know how better the coupling has been done between the coils. So either it may be loosely coupled or tightly coupled. So what amount of coupling has been done can be estimated and known with this formula, that is K is equal to M root of L1 into L2. Okay, so till now we have discussed what is meant by coefficient of coupling, and as well as we have discussed what is meant by mutual inductance, right? So with this, I hope you got to know what is meant by mutual inductance and how we express mutual inductance of any coil which are connected nearby, and also what is meant by mutual inductance when two coils are nearby each other, and also the individual self inductance of those two coils, that is L1 and L2, has been shown to you, and what is meant by coefficient of coupling has also been discussed in this video. And in the next coming videos we'll try to know how we'll write the values of inductances when the inductors are connected in series. Okay, so we can likewise in the resistors and capacitors we can connect inductors in series and parallel fashions. So we'll just try to know how the values vary when we connect either in series or parallel. So what is the expression given to the inductors when they are connected in series, and how the value will be varying in both the circuits, and whether it will increase or decrease, or what are the different types of connections that we can make using inductors will be discussed in the next coming class. Okay, I hope you got the points of mutual inductance and coefficient of coupling in this video. So see you in the next coming videos. Okay, thank you.